Hi there. Welcome to GOAT, greatest overall Altium tutorial. If you don't know me, my name's Jack Woods. I'm going to be running you through this today. Feel free to shoot me an email if you have any questions. Otherwise, let's get started. So, first thing we're going to do is we're going to answer why. I'm sure you want to know why we're doing this. Then we'll go over the general workflow, what gets us from just an idea all the way to a finished PCB design. It means printed circuit board. And then we'll do some quick definitions so all this stuff is a little bit clearer. Then we'll actually get started. We'll open up Altium, make a project file, start adding in libraries. That'll all make sense. We'll make a schematic. We'll start going through the PCB design process. That's got a couple of different steps. We'll go through them one by one, just so it's very regimented, very clear. You can go back and look at a step if it was a little confusing for you. And then, as a little bit extra, we will run through the process of exporting a finished PCB design for manufacturing with a website like JLC PCB or PCBWay or any of the other ones. It's the same process. They all use the same file format. And then we'll wrap up with some additional resources if you're interested and go from there. So, a couple of goals. I'm not going to read all these out. It's a lot of words. You can read and pause the video. Yeah, it's too many words, and I don't feel like it, frankly. So, great. You've read the goals now. We're going to bank on you having read the goals. Very important. So, I'm sure you're wondering, Jack, why do I need to learn Altium? Very simple. It's an industry standard software. 90% chance you're going to need it for work, at least if you're an electrical or computer engineering student. And if you're not, it's still a really good skill to have in your back pocket. It's also an incredibly powerful tool. There's a lot of different plugins you can add to it, some made by Altium, some made by third parties, and they can add a ton of additional functionality. It's almost like its own software development environment too. Like, you don't develop software using Altium, but you could develop software for Altium. So here's a couple examples of things you can do with plugins. Circuit simulation, component sourcing, signal integrity, just to name a few. So for non-EEC students, you'd actually be surprised how easy it is to solve a problem you may have in a non-EEC context with a quick circuit board, especially with how cheap it is to order circuit boards now. I mean, we use JLC PCB for Engineering 100. You can get 5 circuit boards from JLC for like $2. Shipping adds another like $7. Okay, you're still below like $2 a board for, making a small integrated device to, act as a, sensor measurement device, data recording, whatever. Can be really useful. It's good to know. And we also require you to learn it, at least for the classes I'm an IA for. So, if you're watching it for that, yeah, now you know why. So, this is the general workflow. Number one, you got to set the requirements for your project. That's pretty basic engineering design process stuff. You can't design anything if you don't know what it needs to do. Then you're going to make a project file. This is sort of an umbrella file within Altium where everything will be stored. And then this is where you import your libraries of components. Some manufacturers will have libraries, which is just a compiled list of components and their properties, things like that for you to use in your designs. We have one for Engineering 100. We'll go through how you download that and how you import that. And then we're going to make a schematic. This shows us what needs to be connected to what. It's basically like connecting wires on a breadboard. It's very simple. And then you're going to import the schematic to the PCB file. And then doing this will actually place all of your components on the PCB file and show with these small gray lines what needs to be connected to what. Really cool. And then we're going to lay out our components on the board. This is a very important step because the more efficiently you lay out your components, the simpler and shorter your traces can be. What are traces? That's what we're making next. Those are basically the wires that connect all of the components on your board. But instead of being wires, they're traced out pieces of copper on the surface of the board. And then after that, we'll review labels, we'll add holes, and export from manufacturer. So going over our general requirements here, we're going to be designing a power distribution board that connects to a battery and then outputs 3.3 volts and 5 volts, as well as a connection to the battery for measuring the voltage and things like that with your Arduino. It needs to have mounting holes for secure attachment, and it needs to have through-hole components for easy assembly. I designed one last year that was all surface mount. I spent my entire spring break putting them together. We're not doing that again. This time, you can do it. So this is a simplified block diagram of how the board is going to work. The battery is going to go through a protection diode. This makes sure that current can only flow one way. So let's say you flip the terminals of the battery, it wouldn't fry everything on the board. Really cool. So protection diode, it's then going to power the 3.3 volt and the 5 volt LDOs. It's also going to go from there to the board connector. This is where it's going to connect to your circuit board. And then these voltage regulators are each going to power one LED just to make sure everything's working okay. Then they're going to go through another protection diode, go to the board connector. These protection diodes are so if you, let's say, flip-flop a component on the board that this connects to, it doesn't fry this board. Again, very useful, very cool stuff. So that being said, let's hop over into Altium. So this is Altium. You can access it with Kane. It's this one. It's in my recents, as per. So going through downloading the library is pretty straightforward. You go to the Engineering 100 homepage. This may be a little bit different depending on what section you're in and if the layouts for any things have changed. But overall, it's going to be like this. You're going to go to Lab Manuals. You're going to find the Altium lab. Go there. And then we're going to scroll down to Altium to get started. Here's the file. I've already downloaded it for the purposes of this video. So it's already in my downloads. So once we're in there, we can go back to Altium. We'll go File, New, Project. And let's call this Goat. And we're going to store that. I'll just store it right in my Google Drive. We're going to create that. Cool. So now we have this project file. It's .prj PCB. So now what we can do is we can go back to this unzipped folder with all the libraries in it, and we can just literally drag and drop them into the project file. And it's going to need to load for a minute because Altium's slow. We're going to deal with it. I'm going to sit here trying to make noise while it does the thing. Did it work? Cool. Great. Wait. What? Where'd my project go? This is being slow. Oh, okay. So now we can add these to the library. So, or add them to the project, excuse me. So now let's go over what a library is. And to start with that, we have to go over the difference between schematic symbols and PCB footprints. So a symbol is what shows up on your schematic. You'll actually see, if we go back to our slides here, you'll see this is a schematic. This is actually the schematic we're going to be making. So these are all symbols. This is what you can this is what you can see if we go back to Altium. This is a schematic symbol, right? This in this case looks like an accelerometer. So we can click all sorts of different stuff. They're all symbols. But then if we go to PCB library, these are components. This is what actual outline goes on your circuit board, and it's linked to the schematic symbol through the pin numbers. So you want to make sure all your pin numbers align if you're going to be making footprints or schematic symbols. I might actually go through a tutorial on that too. That might be useful. So like we can see, here's one for the Arduino. You'll notice it looks very similar to an Arduino. But then if we go back to the schematic library and we select the Arduino, it doesn't look exactly the same. But this is much easier to figure out what gets connected to what. So now if we go back to projects, we're going to click this and we're going to do File, New, Schematic. Cool. This is where we make our schematic. So now we can actually start putting stuff together. So I want to start with a symbol for the battery. I think it might be in miscellaneous connectors. If it is, that'd be great. No. Okay. So for the purposes of this, we are going to just use a battery symbol, which is fine. That's okay. Cool. So now we have our battery. And this is going to, on one side, be connected to what's called the ground net. So a net is anything, they're small red labels for Altium that show all of these things are connected. So if we go back to the slideshow, we can see this is the ground net connected to the battery. This is the VCC net. So this is battery after the protection diode. So anything with a VCC net label all gets connected together. So like this LDO, that LDO, this board connector. Then we've got the same for 3.3 volts and 5 volts as well. So when we go back here, place a ground net label. And then what we'll do is we will add a protection diode, which we should have in miscellaneous devices. I'm going to look up default diode. Cool. And when you're hovering like this, when you have clicked on a component and you're trying to figure out where to put it, you can press space to rotate it. It's normally very useful. So now the positive terminal of our battery is going through that protection diode that we need. And what we can do then is we can, if you right click on this ground symbol right here, you can see all your different net labels, and you can actually modify these to make them whatever you need. In this case, I want to use a VCC label. So we're going to put that right there. So now we have our VCC net. Cool, cool, great. Okay. So now let's do the I would say let's do the LDOs. So we pull our 5 volt LDO in here, and we can pull our 3.3 volt LDO in here from the Engineering 100 specific schematic library, right? And then we can place our VCC nets on these VIN pins. So this means that the pin 1 and pin 1 on both of these LDOs get connected to this leg of this diode. That'll become important when we actually go to design the board. So then these pins need to be grounded. Ground. And then what we're going to do now is we're going to make 2 new nets for 5 volts and 3.3 volts, like shown in the picture. So the V out from our 5 volt LDO is going to go to the +5, obviously. And then we're going to do, looks like there isn't an option for 3.3. So we'll do place bar style. And then this is actually a good lesson in editing properties. So if you double click on a symbol, or it'll open up the properties tab on this side. And then you can rename things. So like we're gonna call this one 3v3. Cool. And now we have a new net. So now anything with the net label plus 3v3 will be connected. So these are all good. One thing we do still have to do is add our decoupling capacitors. These are capacitors that are attached to either the V in pin or the V out pin, and they're meant to smooth out the ripples, either leaving the LDO or going into the LDO from the battery. So let's go ahead and add those real quick. We should have, do we have capacitors in here? Yep, we do. So that'll go there. I don't really like how that's laid out. So we're going to do that there. And then we're going to do another one on the V out of 3.3. So the data sheet for the 5 volt LDO only calls for a decoupling capacitor to be on the input, not the output. The 3.3 volt LDO calls for a capacitor to be put on the input and the output. So since these are both connected to VCC, we're actually just going to use one capacitor to decouple both of them, which works fine in this situation since the two components are very close together. If you were making designs for parts that are very far apart from each other, you wouldn't want to do that. But in this case, it's totally fine. Oh, wrong button. So if we press Shift and scroll, which one is it? Is it Control? Yeah, Control and scroll. I'm on my Mac on Cane, so it's a little weird. But if you press Control and scroll, you can zoom in, which is always really nice. And we're going to just stretch that out a little bit. Now we can actually run a wire. So if you press P, then you can press W. Now we're making a wire. And this is just another way of connecting things. So we're going to run the positive leg up to that VCC. And we're going to run positive leg over here to V out. Oh, I forgot that's where that connection is. Okay. And then we're going to ground the other sides, as we've been doing. Cool. Okay. So now those are all good to go. They're grounded. Got a little wacky with the zoom. So we've got our LDOs in, we've got our battery in. What do we need next? We should probably do the LEDs, right? So if we go back to components, we look through here. Do we have it in the Engineering 100 library? No, it doesn't look like it. So we'll go to the miscellaneous devices. Just type in LED probably. Cool. We can use LED 0. It's all going to be the same thing anyway. So we'll do one right there. And then we can just copy that. And we'll do another one. Actually, no, we could just do them all up here because we are using net labels. So you notice, again, we are doing 3. And these little side tangent here, these little red squiggly lines are just showing up because we haven't annotated the schematic yet. More on that later. So now we can do our VCC. light, and we'll do our 5-volt light, and again we'll do our 3v3 by modifying this. Okay, so just like in lab, when you have an LED, you have to connect it in series with a resistor. So we're going to go through here and find a resistor. And put that there. That one there. And that one there. Cool. Now we can ground all of these. Great. Now we've got our whole LED set up. We've got our decoupling capacitors. We've got our LDOs. We've got our battery. What's next? As I look at the slideshow to figure out what's next. Oh, you know what? I forgot the switch that turns this whole thing on. So we're going to move that up, and then we're going to delete that wire, which doesn't want to be deleted for some reason. So we're just going to cut it and not paste it. And then we're going to do pin switch. If I can type. I'm not very good at that sometimes. We have one in here. I know we do somewhere. I'm just kind of losing my mind today. Bear with me. Okay, it might be in simulation generic components. Single pole, single throw switch. That's exactly what we need. So then we're going to run this. We're going to put that right there. Select this diode and this net and move those up. Are those connected? We can check by going to pins. Everything looks good to me. So now we've got our switch in place. This is the pull pin switch that you'll see on the boards. Once we pull this, the whole circuit is activated. This is so we don't just kill the battery running power to the board all the time, because that wouldn't be good. So now what we're going to do is we're going to add our connection header. So HDR should be in miscellaneous connectors. Yep. Okay, and we need a 1x4. We got any of those? Cool. So now we'll drop one of those in here. And just so we match up with the schematic I've done already, we're going to have pin 1 be the 5-volt, and pin 2 will be the 3.3. And I'll do these with wires just so you can see how that goes as well. Just from the diode into the pin header. So we put that there, and then we'll run pin 4 is ground, yep. And pin 3 is VCC. Great, okay. So now we can just run those wires like so, and run that up to there, run that right there, and then again we'll do net labels because they make everything look a lot simpler. It's a lot cleaner. It's much easier for somebody to read through your schematic and either see what's wrong or just generally understand what's going on when you use net labels. If I did not make net labels at work, people would get mad at me. So I think that's it. I think that's our whole schematic. It, looks like the design that's on the slideshow. So now what we can do is we'll go to Tools, go to Annotation, Annotate Schematics, and this should all be correct. Go all on. Update changes list. Okay. So now these all have something, except for these, which are being weird. So we're going to accept changes, validate changes, execute changes. That's going to take a second. Then we can close that and close that. And look, now we have U1, and instead of D question mark, we have D3 and D1 and D2 and D4, D5, D6. So now we can actually designate everything. So except for these capacitors, which appear to be a little bit weird. So what we can do for these is we can just name them manually. So this one we'll call C1. And this one we will call C2. Great. Okay. So now everything's done there. So next step, we're going to obviously save this, and we will call it goat schematic because it's greatest overall Altium tutorial. And then we'll move on to PCB design. All right, so we've got a finished schematic design. Something I want to point out real quick is I've actually opened up my design files from when I originally designed this project. And if we look at my schematic, you'll notice that the LED indicator for the battery is actually before this diode. That's okay, but it's not great. I just wanted to make sure I pointed out that discrepancy. The reason I've done it this way over here is that, well, let's go back to this actually, and let's run through a hypothetical. Let's say this diode blows. This diode's cooked, doesn't work anymore. If you're just looking at the physical board, you could still see all three LEDs lit up. So you might not think there's a problem, but really none of your other components are getting power. That's a problem. And that's what we're trying to alleviate with having this battery indicator LED after this protection diode. Just wanted to point that out. Great. Now what we're going to do is we're going to make sure that all of our different symbols here are all properly linked to the correct footprint for the PCB. So the way to do that is we're going to go to Tools, and we're going to go to Footprint Manager. And if we go through these, we're actually going to see that most of these are surface mount, which is obviously not what we want. All those LEDs are okay. So we're going to have to go through and change those real quick. So let's do that. So we're going to make that. Awesome. Now, everything is correct. You can see here all the changes we made, just modified a couple. Hopefully we have these all linked properly when we give you the library. If we don't, I will upload a list of what goes with what, and you can practice this step for yourself. So, now that everything is linked correctly, we can go to File, New, PCB. Great. And this is where we make our PCB. So if we go to Tools, we actually go to Design, we go to Import Changes. Oh. That's a little weird. Oh, we have to name it the same thing, don't we? Yeah. I forgot about that fun little one. Yeah. So I'm naming this goat schematic, even though it isn't goat schematic, because I was silly and forgot that in order to import a schematic, it has to have the same name as the PCB document, such as life. So we just validated and executed all those changes, and look at that. We have a whole load of components over here. Check that out. So what we're going to do is we're going to move all of those up here. So this black space is the actual outlines of our circuit board right now. We are going to change that once I can stop zooming around like I'm crazy. And we're going to just pull all of these over up to here. So here comes what's, I would say, my favorite part, doing the actual layout. So let me open up actually the actual design I did, just so we have something to compare it to. So this is my actual design. It's very small. There's a whole bunch of stuff going on. But you can see everything's laid out in such a way that the traces are very straight, or it's very simple to see where they need to go, which not only makes it easier to route the board, but also to debug physically. So if we go back here, I generally like to just sort of start making my layout anywhere on this black space and then go back later and modify the board edges so that it fits around everything. So let's start doing that. And a little side note here, you can see now these little gray lines I was talking about earlier that show that this switch needs to be connected on one side to our battery. This is the footprint I chose for our battery. And on the other side, it needs to go to this diode. So we're going to put this right up here, right in the corner there. Oh, that's a little too far, too close to the edge. So we'll put that right there. And then we'll pull our battery down. And same thing as in schematic. When you're moving a part around, you can press space to rotate it. It's as cool and as useful as it was in the schematic. So would definitely recommend that you do that. It'll make your life a lot easier. And that's what we're here to do, right? So here's our battery protection diode. And you'll notice those designators that we assigned previously, those actually follow these parts, and you can actually print those onto your circuit board. So anything in yellow is going to be ink printed onto the surface of the circuit board. So that allows us to know what parts go where, basically. So here's our decoupling capacitor for the input, right? So we'll put that down here, and trying to think about how I did this last time. I don't really want to just do the exact same design over again. Make it a little bit of a challenge. But I also want it to be close enough that they still resemble each other, obviously. So, if we see on this 5-volt LDO, the middle pin is ground. And this bottom pin here is VCC. So, I'm wondering if it would be best to... Oh, I did the zoom in thing again. I gotta get used to not doing that. Am I zooming in further? What's going on? Okay, there we go. Don't mind me, I'm just losing my mind. I think it would be best to orient this way. And so, actually, you know what we could do is we could move this over here. And you notice that when you move the designator, it still moves with the part, which is really nice. So we can put that there, and we can put that up there. We can actually run that right between them. And then what we can do is we can grab the other LDO and we can put it on the other side of that decoupling capacitor because they're sharing one, right? So we put that there, like so. And what else we got now? We have a bunch of LEDs, a couple of those protection diodes, this header, which will be important. So let's decide where that's going to go right now. I think, how do I have it on the other one? I did it, yeah, just like that. Okay, that's kind of what I was thinking on this one too, is do, okay, so those are going to be, yeah, I kind of like that layout because then we could just grab the VCC right from there and do diodes like in here. It seems like a pretty good plan. So which diode goes where? That diode needs to connect those two things. We can do that one like right there. Yeah, basically this is just a big game of what's that game called? Where you have the cars on the board. Rush Hour. It's like Rush Hour, where you just have to get everything into the right spot and move stuff around until it all goes together perfectly. And that's what I really like about this process. This part of the process, honestly, is probably what switched me from aerospace engineering to electrical engineering. I love designing circuit boards. It's seriously my favorite thing to do. I need to touch grass. I know. It's fine. So we can pop that down. I don't love that. See, it's just part of the fun. Do that right there. Move that designator down to there. We could also just do this one then, right next to it. Actually, we should swap these around because this one has to go to the further pin. It's further away. Just don't love that being there. We could actually move that up there. Yeah, so I'm just gonna keep laying this one out, and then we'll figure out what happens next. All right, looks like we've got a layout. Not my best work, but it'll do the job. So running through everything here. Um, Battery connects here. This is our pin switch. So positive terminal goes in there when we pull the pin. This terminal connects to the protection diode. This is where our VCC net basically starts. Goes input for 3.3, decoupling capacitor, and then we've got the 5-volt LDO. These are our ground pins all through there. 3.3 volt output. We've got our 5-volt output. Protection diodes for both of those voltage lines. All of our indicator LEDs and resistors down here. Pin header to connect to another board. Decoupling capacitor for the wait, C2, isn't that the 3.3 volt? 3.3 volt out, yeah, okay, that's what I thought. I don't love how far away that is from the 3.3 volt output, but for the purposes of this, I think it'll be fine. So we've got our shape here. One thing you will notice is all of this is a little bit bunched up down here. I don't love it, honestly. And a couple things we could do. We could try rotating the resistors 90 degrees. I don't know if that would really fix our problem, though. So what I'm going to do, since we know that all of these are 1 kilo ohm resistors, and we know that this footprint with the rectangle between two holes and no line in the middle is a resistor, I'm going to delete these designators so that we can actually move these closer together. Which you should not do unless you're in a very specific situation like this. And even then, you really shouldn't do it. But I'm here to teach you the right way. And sometimes just gotta do it. Now, this might not actually let me completely delete them. So what we can do is we could switch their layer, or wait, I don't know, there's another way to do this. Maybe this is the omen telling me that I shouldn't remove these designators. I'm not very superstitious, but I'm a little stitious. So we're gonna leave them in. Okay. So next step is gonna be laying traces. All right, we're back. It's time to lay traces. You might notice I look a little bit different. I just got back from vacation. And, I got a lovely surprise when I got back from vacation. I opened up my documents, and I saw this, the PCB document. None of my work got saved. I don't know how that happened. You're going to have to allow me a few minutes to redo everything. Be right back. All right, we're back. We are so back. I redid everything. If it looks a little bit different, no, it doesn't. You can blame Altium, or you can blame me for having a skill issue. Anyways, let's do traces. So first thing we're going to do is, because these are all power components, we're going to change our trace width, which is essentially the width of the piece of copper that connects the two pins that we want to connect. So the way we do that is we go to Tools, and then we go to, where is it? Rules? Oh, wait. We go to Design, and then we go to Rules. My fault. And then in Design Rules, you go to Routing, and then you go to Width. And because, like I said, these are power traces, instead of 10 mil, we're going to run 30 mil. So that's going to be our preferred width, and our minimum width is going to be 15 mil. And take special notice, these are not millimeters, this is mil, which means thousandths of an inch. That's a very important thing in the PCB design world. I personally prefer doing my boards in millimeters, but that's just because I like the metric system more. Anyways, I digress. So 30 thousandths of an inch is going to be our preferred trace width. So now we can apply that, and then we're back to the board. And then what we can do is we can press P, and then we can press T, and that's for placing a track or a trace. And then like we're going to connect this pin up here. So as soon as you click it, it highlights just the pins you want it to connect to. And so then we just click that, little green circle pop up, boom. That's how you run a trace. It's that easy. And then, so this is going to be a 2-layer board, which means we have a layer of copper on the top and then a layer of copper on the bottom. So if we want to run a bottom layer trace, what we can do is we can switch over to the bottom layer over here and then do that same thing, P, T, and then like let's say we want this to be a bottom layer trace. Boom. And now you can see these traces can actually run over each other. If we go, like if we try to run another bottom trace over this, it's just gonna not let us. So now it's time to just keep running traces. All right, so now you can see we've routed all of the traces except for ground. Why no ground, you may ask? Well, that's because we're going to add our ground pins. We're going to connect our ground pins together with what's called a polygon pour. Now, a polygon pour essentially covers a whole area except for where the traces are with copper and gives it one common connection. So it's great for grounds. So the way you do that is you press that little button, and then we're going to do the outline that we need. So we're going to have it be go right to there, and then we will right click, and then we'll go over to properties. Oh, after we press escape. And we will assign that the net ground. And then we will re-pour that. Boom. So, as you can now see, it's left all of the traces to themselves, right? But it's made these little itty-bitty connections around the relevant ground pins. So now everything's properly grounded. So this is what your board should like this is what your board should look like after you're done running your traces. If it doesn't, come find an IA or ask for help. And yeah. All right, so now that we've traced out our whole board, everything's connected. Now we have to actually define the size of our board. Currently, the software thinks that our entire board is this whole black outline. Obviously, we don't need that much space because we're good at packaging components together. Go us. Okay, so how we're going to fix that? What we're going to do, the way I like to do it at least, is to select all of the components and then move them, if it lets me move them. Okay, it's not going to let me move them. So, the way that we're going to actually make our board the correct size is we're going to go into a different editor. Now, the way we do that is you press 1 on your keyboard, and then we're going to go over to Design, and then we're going to go to Redefine Board Shape. Actually, we're not going to redefine the board shape. We're going to just edit the board shape. Cool. And then we can bring that line, lagged a little bit, go down to there, and we can do that. Oh, that's annoying. I'm very particular about all my boards being perfect rectangles, so I don't like when one of the vertices gets messed up like that, but it's fine. I'll just deal with it. Okay. Cool. Now our board is the correct size, even though the polygon pour doesn't look exactly square on it. That's fine, because everything's still connected. And we can go back to the editor we were just on by pressing 2. And now we're there. Boom. Okay, so now we're going to add some mounting holes. Okay, so to add mounting holes, there's a couple of different ways you could do it. The first is you can use the design option, go into board shape, and then define a board cutout. I don't think that's a good way to do it. Personally, the way I like to do it is go to this, right click, press pad, and then we're going to place that on our board actually. And then we're going to go to properties, and it's already on net ground, which is good. And we're going to go down here, and I'd like this to be, let's say, I want it to be a 2 millimeter mounting hole. So I know, just off the top of my head, you don't need to know this. I know that 2 millimeters is about 80 mil. So we want the size of the ring around it to be 120 mil. And then we're going to make this 80 mil. Cool. So now, this is how you see most mounting holes done on circuit boards. And that's because you have this little protective ring around the mounting hole, and it's grounded, which means that whatever screw or bolt you put through there is also going to be grounded. That's great, because otherwise you could end up damaging your components. We don't like that, as you can tell by the numerous protection diodes. So we're going to do one more of these, and I like to have them in a line. So I'm going to look at what the X coordinate is of this before I go ahead and place it. So it looks like this is at 2,210 mil. So now I'm going to copy that. I'm going to paste it down here. If that works, maybe it doesn't. Oh, there we go. I forgot you have to like set your pivot point when you do that. So there we go. Okay. Let's hope I didn't just do multiple. Nope. Cool. Okay, so that was at what? 2210? Yep. Turn it back over here. Great, so now they're perfectly in a line. And why we want to have these is so that when this gets compressed onto your board, we make sure that it stays very well connected and it's completely constrained. Because if it isn't, and it flies off for some reason, your whole payload loses power. That's bad. So it's very easy to add mounting holes. It's a great way to just make sure everything's taken care of. And now we're going to add some labels. So you can see on the layers down here, this is called the top overlay layer. And this is that white writing that you always see on circuit boards. So if we go to like the 3D viewer, this is what your board will actually look like. You can find this by pressing 3 on your keyboard. So all this white writing, these are obviously to label your components. I did move the resistor labels into the holes of the LEDs because I felt like it, and it let me keep everything more bunched up in here. So what we're going to do is we're going to press text, and we're going to rotate that to put it right there. And then we can edit this, and we're going to make it say goat board V1. Look at that. Beautiful. So now we know how to add labels. We know how to add mounting holes. We've traced out our board. Not a whole lot left to do. We're getting close. Okay, so the very last thing we're going to do with this is we are going to run what's called a design rule check. Remember how when we set our trace width, we went into this rules menu up here? So what the design rule check does is it makes sure that your design follows all of the rules set in there. Everything's connected properly. You don't have any clearance issues between components, stuff like that. Very useful thing to do. You should always run it on your boards. I didn't once, and the board came out really badly. Learn from my mistakes. So we go to Tools, open Design Rule Checker, and then all of these settings should be fine. And then we're going to run Design Rule Check. Cool. And you can see we do have 12 rule violations. Oh no. But if we actually look at what they are, we can see they are silk to solder mass clearance and silk to silk. So what that means is if we go down here, and you can actually click on any of these and it'll show you directly where they are on the board. So like if we click this one, we can see that's just an issue with the footprint, which is what we'll find that actually all of these silk to solder mass clearances are, and manufacturers normally don't have an issue with them. So that's going to be fine. And then if we look at our silk to silk clearances, same gig, again, less than 10 mil. I mean, we could move that a little bit, I guess. That's fine. Hopefully it doesn't then give us a rule violation there. That'd be awkward, right? And then we can look at this. Okay. Yep, same deal. Those, you know, pesky designators. Cool. So now that we've made those changes, we can go ahead and rerun the design rule check. How did we get... Did we get one more? You're joking. Or wait, were we at 12? I don't remember. I don't even know what day it is anymore. It's fine. I'm fine. Everything's fine. Okay, same thing. This is fine, though, because it didn't give us any critical alerts like something is unconnected or there's a short circuit. So this is actually good to go. Congratulations. You just designed your first circuit board. Stick around for some bonus stuff, though, because this isn't the end of the road with these. Okay, so now what we're going to do is we're going to turn this into both a symbol and a footprint so you can place this board on your own board. Now, full disclosure, this won't actually be the board you use. I've designed one that's slightly different, but the process is the same. It's still good to know. So the way I like to do it for the footprint is literally just select everything, Control C, select your origin point, and then we're going to go over here. I've already pressed add component, and then we're going to Control V. Cool. So now what we can do is we're just going to go to top overlay, and we're going to make a rectangle that is exactly the shape of the board. And we don't actually need all of this stuff, so we could just cut that all out. All we need is the mounting holes and these pin headers. That's pretty much it. So we're just going to go ahead and select all this stuff. Keep getting rid of it. Actually, wait, there's a tool for this. We go to Tools. There's an unroute all tool, but that might only be in the PCB editor. So, yeah, whatever. That's fine. Oh, need that. Take care of that, take care of that, take care of that. And look at that. We have a footprint. Awesome. Now we can just save that. And we'll actually rename it. Just so everything looks nice. If it's gonna let us. I think my internet's bad because my cane has just been lagging terribly today. What we would do is we would go back and rename that. I don't think it's that big of an issue for now though. So now, oh, wait, is it gonna let us? Okay, it actually is gonna let us, so. Goat board V1, check that out. Cool. So now we go over to our schematic library, click that tab, we're gonna do add, we're gonna call it goat board, and same deal, we're pretty much just gonna make a rectangle. And then we're going to start adding some pins to it. And made that a little bit too small, so we're going to bring that back down. And then we're going to alter all these pin properties. So we're going to make that pin 1. And pin 1 is actually it's 5 volts. It's going to be pin 2, which is going to be 23 volts. Pin 3 is VCC. And last but not least, pin 4, there's our ground. Cool. So now we have not only a footprint, but also a symbol that you can directly place into your schematics for your main payload board to use these components that we've just designed. Great. All right, so last but not least, we are going to go ahead and actually export this board design into a format that can be read by circuit board manufacturers. So the way we're going to do that is we're going to go to File, Fabrication Outputs. We're going to use Gerber files, which is industry standard stuff. Plot in millimeters. Use the file name. These are all pretty run-of-the-mill settings, so we'll do that. Cool. And now this opens a Camtastic file, which is just a viewer for our manufacturing files. The one thing that we do still need is we need our drill files to tell the manufacturer where all of these holes go. So we go back to fabrication outputs. We're going to go to NC drill files. We'll do... we can do 4 to 3. And then the rest of this looks correct. Okay. Cool. So now we have this other file showing where all of the holes are and of what size. So if we go back over here Now we're going to have our project outputs, and we can take all of these except for the design rule check that we ran earlier, and we're going to compress them to a zip file, and we're going to call it production outputs. Cool. Okay, so now what we can do is, let's say we wanted to actually go ahead and order this board. We can go to, my personal favorite is JLC PCB, because they're really cheap and they do good work. And we're going to just go to add Gerber file. And actually, wait, we can just drag and drop this, can't we? And boom, there's our board. And this website also has its own dedicated Gerber viewer, so you can take a look at everything. I don't feel like logging in right now, so we're not going to do that. So we've uploaded our file, and look at this. For 5 boards, it's $2. Wicked cheap. This is why learning circuit board design is such a good skill to have, because any electronic solution that you need, you can use a circuit board to package it up in a very small fashion and make that solution for very cheap. And this website also has all sorts of different options you can go through to change things. Like I've had to order epoxy filled in cap vias before. We can specify where the order number goes, all sorts of fun stuff. So really, really powerful. And that's all I've got. Make sure to like and subscribe, I guess. I'm kidding. Hope you enjoyed it. Hope everything was useful. Go make some circuit boards.